Hello, and welcome to this quick take video on advanced timing exceptions. In this session, we'll cover recommendations for constraining multiple cycle path constraints. We will explain in detail what these constraints are and also see a few examples. This quick take assumes that you've created clocks in your design. Clock creation is covered in the quick takes titled Creating Basic Clock Constraints and Creating Generated Clock Constraints. Please see those videos if you need more information. You can also refer to the other quick take videos titled Advanced Timing Exceptions, which explains in detail various timing exception constraints. By the end of this session, you should be able to understand and apply the multi-cycle path exception constraints in your design. So, let's get started. We'll start by reviewing the different types of exception constraints. We will then look at the multi-cycle path constraints in detail. Later in this session, we will cover a few tips and guidelines for properly constraining multi-cycle paths. Finally, we will summarize what was reviewed in this session. Timing exception constraints are needed in areas of the design where the default setup and hold checks are not valid. Another reason for adding exception constraints is to direct the Vivado synthesis and place and route to focus on the real critical areas in the design. In the absence of timing exception constraints, and since Vivado is timing driven, there is a possibility that the tool will focus on the paths which may be invalid. Omitting exception constraints will cause the tools to work overtime to optimize the invalid paths instead of the real paths, wasting runtime and device resources. The exception constraints are the set clock groups, the set false path, set multi-cycle path, the set min-max delay, and the set case analysis constraints. In this session, we'll cover the multi-cycle path constraints in detail. Why are multi-cycle path exceptions used? Sometimes timing paths with large delays are designed so that they are permitted multiple cycles to propagate from source to destination. Unlike false paths, multi-cycle paths are invalid and must be analyzed, but against more than one clock period. The multi-cycle path exception relaxes timing on those long paths so that the tools can optimize according to more realistic requirements. Be aware that multi-cycle path exceptions in XDC affect both setup and hold requirements. To help us understand how setup and hold checks are affected, let's first review their default behavior by the timing analysis engine. Setup checks are measured from the source clock edge to the destination's next clock edge. Hold checks are measured from the source clock edge to the destination's same clock edge. Another way to look at this is if the setup check is performed at the destination clock edge n, the hold check is performed at the n-1th edge of the destination clock shown in the figure. This is an extremely important concept that needs to be understood. In the previous example, we examined how the timing engine performs the default checks for setup and hold. Now, let us examine the consequence of applying a setup multi-cycle path of n and its effect on the hold check with the help of an example. Let's say that a multi-cycle path setup of n was applied. If no explicit hold multi-cycle path is set, the default hold check will be performed at the n-1th edge of the destination clock. In order to meet new hold requirements of n-1, additional buffers will be added by the P&R engine. The additional buffers added to the design are unnecessary. The utilization increases and hence power, area, etc. also increase. Typically, you'll only want to move the setup edge to the nth of the capture or destination clock. The hold check needs to be at edge 0 of the capture or destination clock. In order to do this, you need to specify both the setup and hold multi-cycle path constraints. For the setup, specify the startup edge at n. In order to move the hold check back to edge 0 of the destination clock, you have to apply a multi-cycle path hold constraint with the value of n-1. Now the hold check is at rising edge 0 of the destination clock. The guideline here is to remember that you need to specify both setup and hold multi-cycle path constraints if you want correct analysis by the timing engine and the P&R tool. In this example, the default check by the timing engine has resulted in a setup violation. The hold check is passing, But in reality, due to the path requirement, the setup check is actually a multi-cycle path, and the setup checks need to happen at the second rising edge of the capture clock or destination clock. When the only setup multi-cycle constraint is specified, the tool will check hold at the first rising edge of the clock, and now the hold is falling. The user now needs to move the hold check back to the 0th edge of the destination clock. So in addition to specifying the setup multi-cycle path of 2, the user would also need to specify a hold multi-cycle path of 1. With both a setup multi-cycle path of 2 and a hold multi-cycle path of 1, the timing is now passing. In this example, the capture clock has a small positive phase shift. Due to this small positive phase shift, the setup requirement is impossible to meet, and hold requirement is too optimistic. What do we do in such a situation? The solution to our problem is to design a clock enable signal that will allow us to sample the data at the next rising edge of the capture clock. We would need a setup multi-cycle path of 2 and a hold MCP of 1. In this example, the capture clock has a small negative phase shift. The default checks for setup and hold are shown by the blue and red arrows. In this case, there's no need for any MCP, and the default checks are correct and valid. In the case of a transfer from a slow clock domain to a fast clock domain, the default checks for setup and hold are as shown. While the hold check is typically not an issue, the setup might fail due to the tight requirement. In such cases, multi-cycle path constraints are needed for both setup and hold. If you notice the waveform, the data from the slow clock is valid for 3 fast clock cycles, so a multi-cycle setup path of 3 is applicable. With only a setup multi-cycle of 3 specified, the hold check is at edge 2 of the capture of destination clock. A hold multi-cycle constraint of 2, along with a setup multi-cycle constraint of 3, will move the hold check back to edge 0 of the capture clock. For slow clock to fast clock multi-cycle path transfers, use the -end operation to specify the setup and hold multi-cycles. You'll need to specify both setup and hold multi-cycle path constraints. When data is transferred from a fast clock domain to a slow clock domain, the default checks are typically invalid. Depending on what situation exists in your design, you will have to move your setup and hold edges. In this example, the setup edge needs to be moved backwards by 3 with respect to launch clock and hold edge by 2. You'd specify the MCP for both the setup and the hold with a -start option. The guideline for specifying MCP for a transfer from a fast clock to a slow clock is to use the -start option for both setup and the hold. In this case, use N and N-1 from the launch dock with the -start option for both setup and hold. Here we will specify the multi-cycle path for setup and hold using the enable signal. This example assumes that the sequential cells on the clock enable net are in the multi-cycle paths. In the XDC file, create a tickle variable called ncells that will contain a list of all the cells connected to the clock enable net. The multi-cycle path constraint is then specified by using the list of ncells for setup and hold as shown. In this session, we reviewed the exception constraints and discussed in detail the set multi-cycle path constraint. We reviewed various scenarios for correctly constraining multi-cycle paths for setup and hold, important guidelines, and examples. Thank you for watching.